Alright, we are continue. Look at that Docker-based projects, and this title establishes the theme of this entire section as containerized execution for Mlflow projects, meaning the project runtime, dependencies, and execution context are fully defined and portable. Okay, and let's start. Right under that title, the sentence about reproducibility and portability defines the goal Docker usage here, which is consistent execution across machines, across teammates, and across environments such as local laptops, cloud VMs, and CI systems. Okay, and now we move into the configuration panel. ML project with Docker signals that this is an ML project file using Docker as its execution backend rather than Conda. And this name field assigns an identifier to the project, and this identifier becomes the label used by Mlflow when tracking runs, organizing experiments, and displaying executions in the UI. Okay, now look at this. This block defines the runtime container, and this block acts as the contract between Mlflow and Docker, specifying exactly how the container should be launched. So here the image fields points to a Docker image tag, which means Mlflow will pull or reuse this image and execute the project inside it, ensuring the same OS, Python version, and system libraries every time. And volume. The volume's configuration mounts a host directory into the container, and this mapping connects external data storage to the container's internal file system. So training code can access data without breaking them into the image. And the environment list here injects environment variables into the container runtime, and these key value pairs and are used to pass credentials or configurations values into the training process at execution time. And the entry point section defines executable commands for its project, and each entry point behaves like a callable function that Mlflow can run. So the main entry point represents the default execution path, meaning this is the command Mlflow runs unless another entry point is specified explicitly. And the parameters block declares configurable inputs, and each parameter here becomes a command line argument exposed by Mlflow. So the data path parameter is defined as the path type, which tells Mlflow that this parameter refers to a system location rather than a scalar value. Okay, and the apex parameter is defined as an integer with a default value of 10, which means the training loop length can be controlled externally without editing code. Right, and the command string defines the actual execution commands, and Mlflow substitutes the parameter placeholders with runtime values before launching the process inside the container. And look at that, we shift to the Docker file section, and this command signals that what follows defines how the Docker image itself is built. And this base image line defines the operating system at Python runtime, anchoring the container on Python version 3.9 with a slim Linux distribution. And that the work clear instruction sets the working directory inside the container, and every subsequent command executes relative to this path. Okay, and look at that copy requirements txt. This copy step brings dependency definitions into the image, preparing them for installation. and that the pip install command installs Python dependencies directly into the container environment, locking library availability at build time. And that this instruction copies the project source code into the container, making training scripts available at runtime. At entry point defines the default executable, and setting it to Python means all subsequent commands execute as Python invocations. Now, we now transition to the best practices section, and this heading introduces operation guidance rather than configuration syntax. Okay, so let's look at that box. This highlighted area groups recommended behaviors that improve reliability, reproducibility, and maintainability of Mlflow projects. So version dependencies, this guidance establishes that exact dependency versions should be pinned so executions remain consistent across time. And parameterization line, this rule states that configuration values belong in parameters, which keeps code flexible and reusable. And that documentation, this guidance establishes readme files as the communication layer for explaining purpose, parameters, and outputs. And this statement defines data paths as parameters, which ensures portability across machines and environments. So this practice defines logging as a first-class concern, ensuring metrics, artifacts, and outputs are consistently captured. And this guidance establishes robust error handling as part of project quality, producing clearer failures and faster debugging. And modularity here, this line defines modularity as splitting workflows into entry points, enabling testing and reuse. And finally, testing here, this recommendation establishes test entry points as validation steps before production execution. And what are the common pitfalls? Let's look at this. First, this warning explains that relative paths introduce execution ambiguity depending on launch location. And look at that. Here, this line highlights environment completeness as a requirement for successful reproduction. And three, that warning identifies credentials embedded in code as a security and portability risk. And this line establishes clean environment testing as the validation step for true reproducibility. And finally, this warning defines environment separation as necessary to avoid accidental production failures. Okay, and let's look at that. Mlflow models here as a standardized packaging format that decouples training libraries from deployment targets. So that introduces the structure used to represent an Mlflow model on disk. And model format, what's that? This line establishes an Mlflow model as a directory containing arbitrary files plus a central ML model descriptor. So we have diagram. And this diagram frames the visual as a directory level breakdown of a saved model. And look at that model directory box. So the outer container represents the model directory, which is the atomic unit Mlflow moves, stores, and deploys. And descriptor, the ML model file defines metadata such as flavors, environments, and signatures, acting as the entry point for loading the model. And model files here, this section contains serialized model artifacts such as pickle or h5 files. And conda yam or requirement blocks. This block defines the runtime dependencies required to load and run the model, and that this optional file represents custom Python logic used to by the PyFunc flavor. Okay, that's done also, and now we move into a concrete ML model file example grounding the abstract structure in actual fields. Okay, so what's happening here? The artifact path defines the subdirectory where the model artifacts live relative to the run. And the flavors block defines how different frameworks load this model. And this flavor defines a generic Python callable interface enabling standardized inference. And the environment or env field references the dependency file required to execute the model. Load module, that's this field defines the Mlflow module responsible for loading the model path. Here, this field identifies the serialized model file version line. This value records the Python runtime version used at training time, and scikit-learn here flavor block. This block defines scikit-learn specific loading behavior, and that serialization format that specifies Cloud Pickle is a serialization backend. A scikit-learn version, now this value records the library version used during training. Model UUID, what is that? This identifier uniquely labels the model artifact. And run ID, here this field links the model back to its originating Mlflow run, and signature section, and the signature block defines the input and output schema. So inputs here, each input entry defines a feature name and data type, and outputs here, this defines the output data type produced by the model. So UTC time created, this timestamp records model creation time for traceability. Okay, and what is next? Model flavors. Okay, so now we move into model flavors, which define framework specific save and load logic. And look at that. This paragraph defines flavors as adapters that make models usable across tools. And scikit-learn, this card represents the scikit-learn flavor supporting estimators with automatic signature inference. TensorFlow and Keras support, enabling saved model and Keras formats. PyTorch here that defines creating boosting model support with native and wrapper formats. And here you can say XGBoost, like GBM and PyFunc, interface supporting custom inference logic. And what is signature? Let's look at this. That define input and output expectations. So here, this selected line establishes signatures as schema definitions used for validation and documentation. So here I will introduce practical code for logging models with signatures, and here import lines, these imports bring Mlflow, scikit-learn, and signature utilities into scope. And then training, this code block defines a data frame of training features and a corresponding target vector. So random forest regressor, and this line instantiates a random forest regressor with 100 estimators, and model fit. As always, you know that design trains the model using the provided data, and predictions are generated and passed to infer signature, which automatically derives input and output schemas. And start run that part. This context block starts an Mlflow run for logging artifacts. And where is here? What's happening? Look at that. Uh, this function logs the trained model along with its signature and example inputs. And look at that creation part. Now, this section introduces explicit schema definition using Mlflow types. And schema and call spec, what are they? These imports enable manual schema construction and input schema definition. This schema defines two double typed input columns and output that defines a single double type output. So finally here, this line assembles the full signature object from input and output schemas.